Hi, this is Peter with CalcBook, and today we're going to be looking at a retaining wall design. So let's do a quick recap of retaining walls, right? We're going to be using ASCE, IBC, and ACI codes for our loading and strength checks, and our stability checks as well. So for stability, right, that comes from the IBC and the ASCE loading combinations. So we have our sliding, we have our overturning, and we have our bearing pressure. And then for strength, that's going to come from our ACI calculations, right? That's going to be the wall stem, both shear and flexure, our wall footing toe, shear and flexure, and that's going to be on the bottom face, right? That's where the flexure is going to occur when the wall overturns to the left. And then on the heel, that'll be on the top face for shear and flexure. And then our shear key, if we have one, we will be checking that for shear and flexure as well. So let's take a look at our problem statement here. We've got a lot of information. We'll bring this up again when we jump into CalcBook. But we are assuming we have a wall here, no shear key. We've got a wall height of 8 feet. We've got a heel soil height of 7 feet, a toe soil height of 2 feet. Our wall thickness is 8 inches at the top, 12 inches at the bottom, so it's tapered or battered. Our footing is 12 inches thick. We have a toe length of 1.5 feet and a heel length of 5 feet. Our material properties for the concrete, 4,000 psi and 60,000 psi for the reinforcement. And then our soil properties, our active soil coefficient is 0.33. Our passive coefficient is 3. Our seismic coefficient is 0.3. And that is going to be an inverted triangle, and we'll talk about that when we get into CalcBook. Our allowable bearing pressure is 1,500 psf with a third increase for seismic is okay. Our coefficient of friction for sliding is 0.35, and we have a 300 psf surcharge on the heel side of the wall. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we got CalcBook open now. So we go and click into our ACI 318 design module, and then we'll go into our standalone designs, and we'll click on retaining wall and get that loaded up. So when CalcBook opens with the retaining wall, right, we've got some sort of pre-filled out values here for some standard height retaining wall. So we've got, a 10-foot wall and some 9-foot soil. So it gives us an idea of what this should look like. We've also rearranged our summary page here. So we've got this image on the left, which will dynamically update as we change our inputs. And then we've got a snapshot here of all of our different failure modes, the demands, capacities, DCR ratios, and then whether or not the check is okay. And you can filter that down by stability or by strength, so you can narrow in on what you're looking for. So let's go ahead and start updating this to our design. So the first thing is we're going to deselect the shear key. We're not going to be using that right now. We do want to have the seismic load, and we are going to be including or utilizing an inverted triangle shape. So if you click on this information button, right, depending on your soil type and your geotechnical engineer, they may recommend a different type of loading diagram for your seismic. For us, we're going to be using the inverted triangle shape, but you can adjust that here if you need to. We'll be using friction for our coefficient, for our sliding coefficient. So for our stem properties here, for our wall height, we're going to go ahead and update this to an 8-foot tall wall. It's going to give us an error here because right now the soil is taller than the wall. So let's just quickly slide down here and update that. So we'll adjust our soil height to 7 feet. And then we can go back and continue updating our wall properties. So the thickness at the top of the wall we said is 8 inches. The thickness at the bottom of the wall is 12 inches. We did not specify the reinforcement, so we can leave that as is, and then we can update it as we get further into the design. So we'll leave everything else there as is. We'll get into our footing properties. So our footing is going to be 12 inches thick. Our toe length is 1.5 feet, and our heel length is 5 feet. So you can see that as we make those changes, right, our retaining wall updates. And same thing with the reinforcement here. We'll worry about that as we get deeper into the design. For our soil properties, right, the soil height above the toe is 2 feet, and the soil height above the heel is 7 feet. We already entered that information. Our active soil coefficient is 0.33, so we can leave that as is. Our passive is also 3, so we'll leave that as is. And our seismic is also 0.3, so we'll leave that as is. Our allowable bearing pressure is 1.5 ksf, and then a third increase gets us to 2, so we can leave that there. And I think everything else is good as is, and we can drop down to our material properties for the concrete, right? We have 4,000 psi concrete and 60,000 psi for our yield strength of the reinforcement. So I think all of that information is good to go. The one thing we do need to update here is the demand for our surcharge loading. This is 300 psf, so we want to change this to 0.3, and we'll click that and see what that gives us. So we can see that we have a sliding issue here. Before we jump into that, let's go ahead and step through the calculations in detail here, and then we'll come back and we will optimize our design. So we'll scroll down here. We have a few different sections now, right? We have our nominal wall demands and dimensions. So if we open this up, right, this is going to give us sort of some of our initial calculations that we need to calculate the demands on the wall. And then we get into our vertical wall demands. This is going to be like the self-weight of the stem, the footing, the soils above the toe and the heel, and then the total weight of all of that vertical loading. And then we get into our nominal wall demands. So we are going to be checking our calculating our lateral surcharge load, right? So taking our 300 PSF times our coefficient, and then times the height of the soil behind the wall. And then everything is done in a unit, 1 foot per length there into the page. So we calculate our active, our passive, and our seismic, and then we run those calculations once more down to the bottom of the footing. So that's going to be for our stability check. So this goes all the way down. You can see that our height of the soil is our HS plus the depth of footing right here. So our HS heel is 7 feet plus the depth of our footing is 1 foot. So we have a total soil height of 8 feet to the bottom of the foundation. And then we recalculate our passive, our surcharge, and our active and our seismic. So those are all the nominal calculations, right? So we can go ahead and close this section, and then we can jump into the two different sections we have for demands, right? We have stability and strength. So for stability, we have our wall sliding, our overturning, and then our bearing pressure for dead and live, and then our bearing pressure for total, which includes the seismic calculation. So if we open up one of these, right, you can see we are referencing the IBC 1807.2.3 for our loading combinations for stability for sliding and overturning. So that's going to basically be 1.0 times all of our factors, except we apply a 0.7 to our earthquake load group. So, right, that gives us a total sliding demand of 2.88 kips. And then we do a similar thing for overturning, right? We have our lateral loads, and then we have the vertical distances to those centroids of those loads. So for our surcharge, it's just going to be the height over 2. For our lateral soil force, that's just going to be the height over 3, gets us that 1/3. And then for the seismic, such as inverted, that's going to be the soil height times 2/3 to get us to that centroid of the load, of the triangle load. We all add that all up, and we have 10.9 kip feet of overturning. And then for the bearing pressure calculations, right, we have a few more calculations to do, right? We want to get the weight about the centroid of the shape, so we calculate some distances there. And then we get our total net moment about the center line of the footing, so we calculate our overturning and resisting moments. We locate those about the center of the footing, and we get a net moment of 4.43 kip feet. And positive indicates overturning to the left, which is what we would expect for a retaining wall. From there, we calculate our footing eccentricity, right? So we just take our moment over our weight. We calculate the kern area. We figure out if we're inside or outside of the kern. And then from there, we can calculate our bearing pressure using our standard bearing pressure equations. And we get a left side bearing pressure of 1.38 KSF and a right side bearing pressure of 0.44 KSF. And then we repeat that process here for our total. So this includes seismic. So we run through the same calculations, right? And then we have a bit more overturning, obviously, with the seismic. So we have 1.64 KSF of bearing pressure on the left side, and then a smaller bearing pressure on the right side, which makes sense because there's more overturning. So once we've calculated all of our stability calculations, we can go ahead and close this section. And then we can open up our strength section, right? And this is where we're going to be calculating all of our LRFD demands for the strength calculations of the stem and the footing. And if we had a shear key, you would see that here as well. So similar concept here, right? We open this up. We have our shear demand on the wall stem, which is just going to be our nominal loads times these factors in the LRFD load combination. And then same thing for the moment, right? And multiplying by the same heights here to get our moment on the wall stem. And then we do similar calculations for the footing, toe, shear, and bending. So that's just going to be the bearing pressure on the bottom of the footing pushing up on the toe. And then for the heel, it's slightly different, right? This is just going to be the weight of the soil as this wall tries to overturn to the left. So the weight of the soil and the heel holding down that heel of footing, and that causes the moment on the top, or the tension in the top of the heel footing. And then on the capacity side, right, we've also separated into stability and strength. So we would get our sliding capacity, which is going to be our friction coefficient times our weight, and then our total sliding capacity due to the passive resistance of our passive pressure. and then our total sliding capacity from that, and our DCR ratio, which is below 1.5 like we saw earlier. So let's keep going here. Overturning capacity, right? Similar concept as we did before, right? We have our overturning x values, so our length from that left point to determine the overturning resistance, and then we get our factor of safety against overturning. And then our bearing capacity is just going to be what we entered in below. So we go ahead and close the stability section here, and we go into our strength, right? And these are all going to be sort of our typical concrete strength calculations that we have from ACI. So we're not going to go deep into those. We've done other design modules with that information. So let's go back to our design summary. Right, we have an issue with sliding. So the quickest way to do this is just to add a shear key and see if that solves it. So we'll just click on Add Shear Key here. Right, and that information will then pop up the key properties box. So we've got a 6-inch deep key, 12 inches wide. We've got number 6 reinforcement at 9 inches. Right, and that is giving us a 0.94 DCR, so that is okay. One thing I want to point out is that some codes, depending on where you are, will require you to include the heel side soil pressure all the way down to the shear key. So you can see right now the passive pressure diagram goes down to the shear key, the bottom of the shear key. But the heel side, or the active side, right, that does not go down to the bottom of the shear key. That stops at the bottom of the footing. Depending on some codes, they require you to include this. So if you were to click on this, it will increase the overall height of your active side diagrams, so putting more pressure on the wall and more overturning and more sliding. And you can see that that causes the sliding to go up. So it's a bit of a game here to try to figure out what works to control these types of failure modes. So from here, if we wanted to increase our sliding, we could try increasing the shear key, but that's also just going to increase our load. So we can try increasing the footing height. That might give us a bit more passive pressure. So we can go down here. Let's maybe bump this to 18 inches. Right, so that got rid of our sliding problem, but now we have a bearing pressure problem because we've increased our overturning moment. So we can maybe lengthen the heel or the toe. So maybe we bump this to 6 feet. And still a little bit of a bearing pressure problem, so maybe we increase the toe length to 2 feet. That might get us down, and that does. So that is a retaining wall design module in CalcBook. Lots of options, lots of decisions to be made here, but it's all pretty straightforward and very easy to navigate through our interface here. If you have any questions or comments or have suggestions for other videos, please let us know in the comments below, and we'll see you next time.